All right. Welcome everybody to the second installment of the two talks that Prabal Adhikari generously promised us to give us to provide a little bit more additional insight into perspectives from Chiral perturbation theory with finite isospin QCD, going deeply into the phase diagram where other tools cannot reach. I won't go into a long introduction. That is what Phil did last time. I'll just ask you to take it away and let's have fun.
Well, thank you again for the invitation to give this talk. I do have to admit that while giving two talks felt somewhat intimidating, the model definitely works really well. Not just from your end, but also from my end, allowing me to think more deeply about the areas that I've been working on. And so here's sort of the review of Chiral perturbation theory. It's a low energy effective theory that describes the interactions of pseudo Goldstone modes. And these are 3 pions if you're looking at the 2 flavor case. Of course, if you're looking at 3 flavors, there's a meson octate that involves the pions, the 4 kaons, and the eta. And I showed you last time that the key building blocks at finite isospin are the Goldstone manifold, which is where the pions live. And then there is a scalar pseudoscalar source, which is how quark masses enter the theory. And then if one wishes to, for instance, examine what the pion condensate is doing in the superfluid phase, one requires a pseudoscalar source. And then the isospin chemical potential itself enters through the 0th component of the covariant derivative. The structure of the covariant derivative is sort of interesting because it's proportional to a tau 3, which is present in the commutator. So if you sort of wanted to explore or ask what a baryon chemical potential does to this covariant derivative, you'll immediately notice that the baryon chemical potential is proportional to the identity, which means it completely disappears from the theory. So this is truly a theory of pions where you can study an isospin chemical potential, but not a baryon chemical potential, for which there are quite limited tools, and it's usually model-based calculations that are most, I would say, useful or advanced in that area. QCD itself is somewhat less useful due to the general intractability of the problem. And the general plan, or the program, I should say, of effective field theory is to capture the symmetries of the underlying theory. As long as one captures these symmetries and takes into account all the relevant operators, one has a theory that is entirely model independent. And so to drive home the point a little bit more, instead of showing you this big effective potential with all these LECs, I decided today to put together this schematic free energy so that you can appreciate what is actually coming out of the theory. So the structure of the free energy in Chiral perturbation theory and at finite isospin, it looks roughly as shown there. So there is an m pi squared f pi squared, which ensures the correct dimensionality. And there's an order 1 contribution, that's the tree level contribution. And then the next leading order contribution has a structure which is of that form. Here, x could be m pi, it could be the isospin chemical potential, or it could be the square root of E times the external magnetic field. And one can ask, and this question came up last time, how big are the size of these next leading order corrections, which is helpful if one wants to understand how the theory itself is converging. So if you choose, say, x equals m pi, then m pi squared over 4 pi f pi whole squared, which is the characteristic scale that shows up, and this 4 pi whole squared has to do with the use of ms bar. One ends up with a ratio that is roughly 1%. Okay, so the contribution of the next leading order contribution term at x equals m pi is 1%. So now you can crank up, say, the chemical potential and take the chemical potential to 3 m pi whole squared, and the answer is that will be roughly 10%.
Just throw in one more question, right? This is it is thermal equilibrium that prevents something else from creeping in here, right? Because if I do dynamical calculations, all manner of kinematic variables would threaten to put some large logs into your order one terms that might rearrange your
Indeed.
kinds.
Yeah, indeed. This argument works at equilibrium, but I think if one wishes to examine um, kinetic theory, for example, then I think there are these pion widths one has to take into account, and they will sort of spoil the power counting. Yeah. Um, and the other thing to note is that, so I've shown you here the next to leading order contribution. So if you go to next to leading order, you'll have a contribution of this form squared, which means you're looking at a quantity that is 10% of a 10% at the maximum chemical potential that I looked at, which is roughly 3m pi. And that's suggesting that doing a next to leading order correction will, is a lot of work, but will give you a 1% result, basically 1% update on the next leading order result. So for that reason, it's not terribly fruitful to keep doing this calculation, at least for the 2-flavor case. In the 3-flavor case, things are a little more tricky because the kaon is involved, the kaon is more massive, and so the corrections are more significant. But 2-flavor Chiral perturbation theory is converging extremely well, and the results therefore should be very reliable, given that it's an effective field theory approach. And this is the conclusion from part one. The top plot shows the conjectured phase diagram from the seminal paper that looked at the phase diagram QCD in a finite isospin chemical potential. There is a phase transition, as I noted, at m pi into a pion condensed phase. This is a superfluid phase. At high temperatures, this phase gets destroyed. At large chemical potentials, there's a BCS type phase, which comes with a gap, and below this gap, there is a pure gauge theory, which comes with a first order phase transition, and is expected that this first order phase transition ends at a critical point. Below here is the status. Lattice QCD has done some fantastic work in nailing down the phase diagram. What I find quite shocking about this plot is the fact that there is this phase transition into the pion condensed phase that is largely unaffected by temperature until one reaches a temperature of about 150 MeV, and then suddenly the second order phase transition line becomes flat, which is quite different from expectation. While Lattice has made significant progress on the phase diagram, as I noted last time, there are things that Chiral perturbation theory can do. For example, inform us about the zero source pion condensate, which is not something the Lattice is able to do so well at the moment. And as I noted, the Lattice also needs to do some work and determine the location of this particular critical point. But things are looking in pretty good shape, which brings me to the key part of today's talk, and that is finite isospin Chiral perturbation theory, but in the presence of a magnetic field. So as a quick sort of overview, there's a sign problem in Lattice QCD, and this sign problem has to do with the fermionic determinant shown here. As long as that fermionic determinant remains real, then one can do Monte Carlo simulations, which is where isospin chemical potential, or Y, can be studied on the lattice. However, there's a large phenomenological region, including finite baryon chemical potential, for which there is a sign problem. And there is no sign problem if there's no chemical potential present, but there is an external magnetic field. However, when both an isospin chemical potential and an external field are present, the sign problem returns. Basically, this determinant loses this gamma 5 hermiticity property due to the unequal magnitude of the signs of the up and the down quarks. And for that reason, the sign problem returns, which means we have to resort to either model calculations or, even better, resort to effective field theory calculations, which I'll talk about today. In order to do this, one basically upgrades the symmetry of the effective field theory to make it local. And the other caveats that one has to think about carefully in introducing a magnetic field is to introduce a magnetic field after first entering the superfluid phase. And the reason this is important is because if one assumes the magnetic field already exists in the theory, that can be in contradiction with how a superfluid actually behaves in the presence of a magnetic field. If there's a charged superfluid in the theory, the assumption that the magnetic field is the external magnetic field is incorrect, because it's possible for the superfluid to create countercurrents and cancel this external magnetic field. So it's important to first turn on the chemical potential, be in the superfluid phase, and then turn on the magnetic field to ask how the system behaves. And one has to be careful about making sure that the thermodynamic limit is well defined. As soon as you turn on the magnetic field, this pion superfluid, which has an electromagnetic charge, will have an energy that basically diverges, right? This divergence can be calculated using classical electrodynamics, and this the size of the electrostatic energy goes like r to the 5. And this is 1/r coming from the electrostatic potential, and then the charges scale like r cubed each, which gives you an r to the 6th, and that explains the r to the 5. In Carl probation theory, however, the energy scales like r to the cube. There's an f pi to the 4th, which is effectively the m pi squared f pi squared I showed you earlier. And then there is an order 1 quantity, again, something I mentioned previously, except now there's also the impact of the magnetic field. What we want to make sure we do is the energy associated with the strong force is much bigger than the energy associated with the electrostatic forces. And thankfully, there exists a window over which that's true. So as long as r squared is less than 1/e squared f pi squared, a quantity that will appear later on as well, we can safely assume that the strong interactions dominate. The equality on the left here is basically the regime of validity of KITP, where 4 pi f pi squared is the relevant mass scale or mass squared scale. And this window is if one does the calculation with the right numerical values, one finds that this window is significant, and therefore the thermodynamic limit exists. The alternative to doing this is to simply add a background charge to cancel the electrostatics, at which point KIPT automatically dominates, and we can proceed to think about the problem. So the Lagrangian now is updated, and it's updated to include the external field.
Let me ask another one quickly, if you don't mind.
Sure.
I've seen a number of strong magnetic background field calculations done in QCD with some rules, and there people generically do an expansion in magnetic fields that are suppressed by where a ratio of the magnetic field to some characteristic scale in the problem is small enough that you can expand in powers of the magnetic field and that ratio. Is that the same perspective that you're applying here, or is this, are you trying to go whole hog here?
Okay, so the perspective here is, so for this part of the talk, I won't be doing any next leading order calculations. So that's the background field is entirely classical. So that's comment number 1. If one uses Carl probation theory to do a finite magnetic field calculation, it has to be the case that the magnetic field is in the same order as the pion mass, roughly, so that you're in the regime where that number is much less than 4 pi f pi, which is roughly 1 GeV. So as long as that condition is satisfied, the effective theory calculations are converging, really well. The other comment is that when a magnetic field is introduced and you're doing a next leading order calculation, one effectively has to take into account the effect of the magnetic field at all orders, basically. So say, so there's a magnetic field line coming from the external source, coupling with a pion. One has to take into account all of those couplings, and that's what I'll do and show in the latter part of the talk where I discuss finite volume thermodynamics. Yeah, I myself haven't done these sum rule calculations. So what is the model in which they're doing these calculations, by the way?
Michael, you did your master's in this.
Yeah, I mean, essentially, in for what I did, you're comparing the scale of the magnitude of the magnetic field to the mass of the, well, in my case, it was a charm quark. So it was, I guess, similar to what you were saying. We in fact 4 times the charm quark mass. So yeah, so that was the condition that had to be satisfied for this expansion to.
Well, they were looking for propagators in that background of a classical magnetic field, but they were in the end expanding in powers of B due to the parameter range that they were going for.
I see. Yeah, so yeah, if one is doing a calculation within an effective field theory setting, then clearly you want your calculations to converge, right? So that's an important condition to think about. If you're doing a model calculation, that condition, I think, is not necessary, right? I mean, unless one is thinking qualitatively about some regime of the theory or some regime of the model where some physics that is relevant lies. Otherwise, in a model calculation, as long as I suppose the mathematics is reasonable, then there are no strong constraints on what the magnetic field can be, what the size of the magnetic field is. But here there certainly is, because of this 1 GeV scale that is crucial to the convergence of Chiral perturbation theory. Thankfully, for this part of the talk, we are not doing anything but looking at the leading tree level effect. So for which the Lagrangian is this one. The only difference from the previous scenario is the introduction of the external magnetic field, which couples to the pions through this V mu. There's the chemical potential, and there is the quark charge matrix Q, where A mu is the gauge field associated with the external background. And so there are a few natural candidates for this analysis, and the idea is to construct possible phases and their Gibbs free energies, and basically compare the Gibbs free energies to determine what the phase looks like. So the most obvious one is one where the superfluid completely expels the external field, and for that the magnetization is negative H, so that B, which is the sum of the external field and the magnetization, is 0. So there's no net field in the system. Then there is the natural possibility of partial cancellation of that external field H, and that happens through a single vortex. Here's a profile for students who may or may not have seen this. So basically, the blue line here indicates the superfluid density. So at the center of the vortex, you should imagine something with cylindrical symmetry, and this being the radial coordinates. At the center, there's a requirement that there's no superfluid density, which increases, and as the superfluid density increases, there are superfluid currents, and that's what cancels the external field, which is why the magnetic field itself is steadily decreasing. And the other thing about this plot is that there is this red dotted line, which is indicating the size of the neutral pion condensate, which which leads to a rather interesting question of whether it condenses in other parts of the phase diagram or not. But nevertheless, this is basically the generic profile of a single vortex, and this unfortunately has to be generated numerically. There's no analytical solution except for the asymptotics. And then the natural generalization of a single vortex is a magnetic vortex lattice, where there are lots of these holes punctured through the superfluid, and that will be the main part of today's discussion. And then if the magnetic field is too large, then it becomes unsustainable to have a superfluid, which means that you end up in the normal vacuum. And this is, not the full picture. There may be other possibilities. Some that have been considered include Chiral soliton lattices, and there's also the possibility that magnetic vortices don't exist in an organized solid-like setting, but behave more like a liquid or a gas. Which brings me to the nature of superconductivity. So when one thinks of superconductivity, the most natural question is whether vortices even exist. So when vortices exist, we call this type 2, and when vortices are not permitted, we call this type 1. So on the right here is a plot of the actual values of HC1, HC, and HC2 in Chiral perturbation theory, and I'll go through these carefully. So on the x-axis, I'm starting at a mu I of m pi, so I'm in the superfluid phase, so I'm ignoring the normal phase that occurs for smaller isospin chemical potentials. And then what I'm exhibiting here is the phase transition line from a uniform superconductor which exists for extremely weak fields. So if the field is really, really weak, there's enough superfluid charge and superfluid current to cancel the magnetic field. That's that phase. On this line is the single vortex phase. And then this you can ignore for the moment because this actually doesn't exist in honest to, if you use realistic parameters, this is not the phase transition that occurs in QCD. And then there's HC2, which is where the magnetic vortex lattice gets destroyed and turns into a normal phase. Okay. And this HC2 is known analytically, and this is because when the vortex is about to be destroyed, one can resort to a perturbative calculation and basically consider the exact dispersion relation and ask when the dispersion relation becomes tachyonic. And this HC2 is this quantity. It's proportional to mu squared minus m pi squared. So a natural question is whether type 1 superconductivity is even allowed in QCD, and the answer turns out to be yes, it is. And then let me sort of give you the heuristic picture. If the transition were type 1, there would be no single vortex. You would have a superconductor phase, and then there would be a straight transition into a normal phase. If the superconductivity in Chiral perturbation theory were weakly type 2, the region where vortices exist would become smaller and smaller and smaller. So in effect, HC1 and HC2 would come together and basically collapse on top of each other. Basically, there's a very narrow region over which magnetic vortices exist. And the reason this heuristics is important is because HC1 is only numerically known. And what we want to do is ask whether it's possible for this HC2 to be below HC, which gives you type 2, or alternatively for HC, maybe I'm saying that incorrectly. So what I actually want to say is, basically, we want to compare HC with HC2 to determine whether the superconductivity is type 1 or type 2. If it turns out that, I'm sort of forgetting the argument here, but basically, if HC turns out to be such that, hold on a second, I apologize for this. So let me go through the argument maybe in this diagram, and maybe the argument will come back to me. So basically, if you compare HC and HC2, you'll find that the ratio of these two quantities is EF pi, okay? And this EF pi is relevant because if this EF pi lives to the right of this m pi, then it's possible that there's type 1 superconductivity. So what this is basically saying is that either the cost of going into the vortex phase is cheaper, or the cost of going into the normal phase is cheaper. If EF pi resides here, then it turns out that it's cheaper to go into the normal phase, which is what happens in this scenario. And if EF pi, on the other hand, is such that it's below m pi, then you're in the normal phase. So there's no superfluid you can convert into a type 1 superconductor. So you're basically left with a type 2 superconductor for that reason. And if I manage to confuse anyone, please let me know, and I'm happy to maybe indulge your questions, which might even help me think through what I actually intended to say.
I wasn't sure if you mentioned why we call it a vortex. Where does that come from?
Okay, very good question. So basically the argument goes as follows, right? If you have a magnetic field going through a superfluid, there is a certain cost attached to that, right? And that cost goes like b squared in the free energy. If on the other hand, you get rid of this magnetic field by creating a vortex, then you can ask whether that is cheaper or not. If that's cheaper, then that's the phase that exists in the phase diagram of QCD. If that's more expensive, then the normal phase exists. So basically, what the game that we are playing is saying, let's assume this phase exists. Let's compute its Gibbs free energy and ask in what part of the phase diagram the Gibbs free energy is actually lower. Does that answer your question?
Sort of. I guess I need to brush up on my thermodynamics.
Well, it's also a geometric thing, right? These things take a shape. There you go. Symmetry in action. That's what I talk about. These things.
It's
Yeah,
so is the point that the magnetic field has sort of got some directionality in this cylindrical thing, so it might be just cheaper, or if the whole fluid moves with the magnetic field, as opposed to sort of being against it, would be like the normal phase where it says that the point, or.
I mean, right. So right. So in a way, you're right. So if you penetrate, the superfluid with a magnetic field, then there's some energy associated with that. But if the system magnetizes and starts canceling it, there are regions of the superfluid where the cost of the magnetic field goes down, right? Okay. That also means, however, that you're creating a normal phase which might be more expensive. So there's this trade-off. So you're getting rid of some superfluid to create a normal phase, right? And that is what enables you to kill the magnetic field. So getting rid of the magnetic field is maybe saving you energy, and maybe getting rid of the superfluid phase is costing you energy. So for that reason, you have to look at the full Gibbs free energy associated with this trade-off and ask what the net cost is. And by looking at the net cost, you can determine what the phase diagram is. So the magnetic vortex analysis is easiest basically near the upper critical point where the superfluid density is really low. Everywhere else, you have to handle this calculation numerically. And even for the single vortex analysis, the analysis is entirely numerical in nature. Thankfully, near the upper critical point, one can do a fully analytical analysis using a perturbative expansion. And interestingly, the perturbative expansion one uses in this setting is exactly the perturbative expansion that you may have encountered in the analysis of a nonlinear oscillator in classical mechanics. The condition is that you want the external field to be very close to the upper critical field. Okay, and that ensures that the size of the Pine condensate is really tiny, which allows for a perturbative analysis to be valid. The challenge is that, unlike the standard abelian Higgs model calculation, in this theory there are neutral pions, which may condense, right? So one has to be careful about not completely ignoring that effect. But for convenience, I'll assume for now that there's no neutral pion condensation. Make sure that we check that the solution that we come up with are stable against that condensation right at the end. And the other difference is that because we're working with a theory of Goldstone modes, the interactions are derivative in nature, which is not what happens in an abelian Higgs model. There, the interactions are all of this type. They're point interactions. Here, there are two types of derivative interactions, one involving covariant derivatives of this type, and then the other one that involve covariant derivatives of pi plus, or pi minus, pi minus. And the equation of motion is quite nasty, naturally. There is the equation of motion associated with the gauge field, and then there is the equation of motion associated with the pion field. However, luckily for us, this is solvable by hand. So here's the game one has to play. So construct a perturbative expansion where the B naught here refers to the external field. And if this external field is close enough to the upper critical point, then the Pine condensate is small. So there's a tiny Pine condensate that you create as a result. And this solution is most easily written in conformal coordinates, which is just a fancy way of saying, oh, use these change of variables so that the equation looks as simple as possible. And because this is in effect a Landau level problem, you have this infinite degeneracy in the solution, which basically means that one has to do more work to determine what the actual ground state is. Okay, and so the solution written here is the solution based on Abrikosov, who obviously was the first person to think about type 2 superconductors. And this ansatz, if you like, is written in the symmetric gauge. There is a variational parameter nu that we'll revisit. And then there's a magnetic length that determines what the vortex lattice size looks like, the periodic structure looks like. The equation associated with the magnetic field, interestingly, can also be solved. And unsurprisingly, there is the B external, and then there are corrections associated with that. You'll notice this interesting averaging going on. These are averages on the transverse plane. The magnetic field is in the Z direction. And this constant in the magnetic field solution is chosen to ensure that magnetic flux is conserved in the analysis. So now that you have the solution for the magnetic field, one considers the perturbative correction to the pi plus. And we don't actually need the explicit form of this, except to appreciate that this solution better be orthogonal to that. And that's what constrains the interaction of the pions, whereby two pions come in and they scatter off at a point. And this average, therefore, now can be written in terms of the average of a two-point function. So basically, what we are doing, what we are buying by this analysis is converting all 4-point averages into averages of two-point functions. And for the final piece, remember, the game is to construct the Gibbs free energy. And for this, we need to write down the Hamiltonian and basically average over all interactions. And there are derivative interactions as well. And so one can convert these derivative interactions into point interactions simply by using the equation of motion. So take the equation of motion, convert it into quantities that are actually easy to deal with, and it turns out that the first type of derivative interaction has this form, and then the corrections are pions to the power of 6. However, the complicated derivative interaction turns out to contribute at an order beyond which we are working, which means we can write down the Hamiltonian in terms of the external field, a two-point interaction squared, and then there's a 4-point interaction there, but it turns out that Abrikosov taught us how to write this in terms of a 2-point interaction, and that happens to what's called the Abrikosov ratio. And this ratio can be computed for different types of magnetic vortices. And so the parameter nu I showed you is a function of this. And the way to think about this particular quantity is as follows. Previously, what I noted is that there's this infinite degeneracy. The key idea is to break that degeneracy. And in order to break it, what one has to do is consider a finite set of the most symmetric solutions. And the reason for that choice is that the expectation is those solutions will likely be the ground state. And in particular, the symmetric solutions, which can be constrained using this coefficient, has this structure. So basically what you do is you take the coefficient and ensure that it repeats. And this is what gives rise to a periodic lattice, which I'll show you in the next slide. And the other thing to note is that the condensation energy, which is the energy difference compared to a scenario where all the magnetic field penetrates the system, comes with a negative sign. And this is good because this is suggesting that the magnetic vortex is stable, more stable compared to the scenario where the magnetic field entirely penetrates the system. And the beta A appearing there is determined by basically looking at the various symmetric solutions. The most symmetric solution turns out is the triangular one. As a quick note, as you increase the chemical potential, the condensation energy is becoming more and more negative, indicating that the solution is becoming more stable. And here is the lattice structure. So this is at an external field that is 1% below the upper critical field. And so what I'm showing here is basically the nature of the vortex lattice, which is triangular, as you can see. It's repeating this way and it's repeating this way. And what you also notice going from plot to plot to plot with increasing chemical potential is that the density of the vortices is going up. So I'm showing you here a region of 0.01 inverse MeV, which is roughly 2 Fermi, by the way. So basically going from the center to here is 2 Fermi, which means the box is a 4 Fermi by 4 Fermi box. And the solution has an analytical form due to its periodicity in terms of the Jacobi theta function, which obviously is famous for this periodic behavior. And you'll notice this quantity C, which is the C sub n that I showed you earlier. What's interesting about this quantity is how it vanishes when B external is exactly B critical, which means the solutions here will become completely flat if you're right on the upper critical point. So with these solutions depicted, I should mention that the neutral pion may condense. In fact, there are certain circumstances in which it does, but because you have a lattice with a superfluid density and holes,
just on the previous slide, you said that your C coefficient, your field becomes uniformly flat when the external reaches the critical. What is the actual physical interpretation of that? Is that now your superfluid is broken, or?
Okay, that's a great question. So the idea is that for you to have a lattice, these vortices must be interacting repulsively, right? So you're forcing these superfluid pions into some region of space, and you're forming this magnetic vortex structure. At some point, the repulsion between the magnetic vortices becomes so strong that it's better to kill the superfluid entirely, basically. So as you approach this external field, these repulsive interactions will start dominating in effect, and that's what gets rid of the type 2 superconductor.
Now let's just ask a question on this slide. So, what sets the scale for these vortices? Vortex?
That is a great question. So there's a characteristic magnetic length associated with the vortex lattice. So if I go back to the original solution I wrote down, what you'll notice is that this solution comes with a parameter that determines the shape of the vortex, and then there's a length parameter that determines the size of the vortex. And this length parameter is completely correlated with the external magnetic field. The expansion is, remember, one around solutions near the upper critical point, right? So in that sense, the external magnetic field also depends on where that line lives, and the location of that line depends implicitly on the choice of chemical potential. And so the magnetic length is due to the magnetic field, which in turn depends on the chemical potential. So if you look at the size of this, so that would be LB, except for this normalization factor nu. So it's LB divided by nu is the length of that. Okay, and the same going this way. And so as you crank up the chemical potential, the magnetic length is becoming smaller and smaller for the obvious reason that the critical field is going up, which means that you expect the length itself to be going down.
And 45 degrees is already baked into the solution that you showed us previously, right? Z mod squared plus Z. Yeah, all right.
Yeah. So I think I have about 15 minutes, is that right?
Yep.
Okay, so since I have 15 minutes, let me not maybe spend too much time on this part, partly because I feel like the finite volume thermodynamics piece is quite intriguing. But let me just make a quick note that one does have to be be careful about making sure that the neutral pion doesn't condense. And in effect, this amounts to solving a Schrodinger equation with the vortex as a background. And because the superfluid density is entirely positive, you expect the delta, which is basically the energy levels that appear in this vortex, you expect that to be positive, and for this reason, we believe that the neutral pion at least doesn't condense near the upper critical point. Of course, there's a much larger phase diagram, and analytically, it's not possible to explore this phase diagram. So there are still regimes within this phase diagram, including a finite temperature where the neutral pion may condense. And there are intermediate regions of the chemical potential and magnetic field for which the neutral pion may condense. So we can definitely say that there's no condensation on this line. Everywhere else, we are unsure, and so that's an open question, if you like, that might be amenable to numerical tools, but certainly there are very limited analytical tools available currently. And with that, let me conclude this section and talk about the impact of a magnetic field, I'll discuss the scenario in the absence of a chemical potential, which is a rather intriguing topic, because lattice QCD of magnetic field has been done for the last 15 years, and until relatively recently, until this work in particular, I mean, the thermodynamics associated with this particular system hadn't been investigated. So the key question here is basically the following: what are finite volume effects on observables and condensates in a uniform magnetic field? In particular, what does the Chiral condensate do in a finite volume? And what we know about the Chiral condensate in QCD is that in a magnetic field, quarks are forced to live within the Landau orbit. So basically, the quarks are being squeezed, and this is often referred to as dimensional reduction. And when you reduce the dimensionality of a system, typically the pairing you expect becomes bigger, because there's less space, if you like, for the quarks to be perturbed in. So the Chiral condensate basically increases in size as you increase the magnetic field. In addition, there is a magnetization. So even though the QCD vacuum is, in quotes, empty, there are virtual pairs of pions that can pop up in the vacuum, and that means there is this electromagnetic interaction between the pions and the external magnetic field, which basically magnetizes the vacuum, and that's measured through a pressure anisotropy, as I'll show you in just a moment. And then the other quantity that I'll look at is the neutral pion magnetic polarizability. So basically, the neutral pion interacts with the magnetic field because of virtual pi plus pi minus. This means that the energy, the mass of the neutral pion is impacted, even though the pion itself doesn't interact directly with the external field. And this is a quantity that can be measured on the lattice. And the natural question is, what is the size of the finite volume correction? And we're going to do this in Chiral perturbation theory. So the tool is exactly the same. And again, the results are entirely model independent. And because we're in the finite volume, we have to choose a boundary condition. Periodic boundary condition is the most conventional choice. And then it's also natural to work in Euclidean space. So I'll be using this particular convention with 0 appearing in the first place. And then I'll use the fully asymmetric gauge that is not the Landau gauge, that depends on the second spatial coordinate. So that's the big, if you like, setup for this part of the talk. So the first thing to note is that if you take that gauge field for a uniform magnetic field and you go, say, around the second spatial direction, what you'll notice is that the gauge field changes as you go around the box, and this change is a gauge transformation, and this gauge transformation is encoded in this quantity, okay? So this theta here is a constant, and this derivative doesn't care about the theta. This is what's called a twist angle. And then this lambda 2 is basically this minus BL2 multiplied by x1, okay? Because there is a gauge transformation of the gauge field, in order to preserve gauge invariance, we want to impose a corresponding gauge transformation on the pion field. Okay, so basically the idea is that if you're in a periodic box, you better check that gauge invariance is preserved. Okay. So what is the consequence of preserving this gauge symmetry? And it turns out that the answer is magnetic flux quantization. So what I've shown you here is how the pion field transforms as one loops around a box. So there's a Wilson line W2, which depends on coordinate x1. So now what I want to do is I want to go around the box, either going in the first direction first and then the second direction second, or vice versa, right? You end up at the same point in doing this. If you choose to go in the second direction first, the Wilson line depends on the first coordinate, which is x1 plus L1 in this case. And then you go around the box in the second direction, that picks up a trivial gauge transformation with a twist, and that also appears in the opposite ordering. However, because you're going in the x1 direction first to pick up this phase, here the W2x1 is the same W2x1 that appears over there. Okay. If the solutions are to be unique, then this W2x1 has to be the same as the W2x1 plus L1. And that is only true if the magnetic field is 2 pi n phi, which is an integer divided by the transverse area. So magnetic flux is the fundamental entity in a finite volume, not a magnetic field. The alternative way of saying is that magnetic fields are quantized in the box, so you cannot choose an arbitrary magnetic field for a particular box. These are fixed. And this, interestingly, has echoes of a magnetic vortex, even though the two are obviously different topics, at least for the purposes of this talk. And the other really interesting aspect of this problem is the fact that the Green's function in a magnetic field is not translationally invariant. Okay, and this will become important when one considers how a Chiral condensate behaves, which I'll show you in the next plot. So let's first look at the Green's function in infinite volume. Remember that we are in a magnetic field, which means that this operator has a gauge embedded inside it, and that gauge is naturally translationally non-invariant. This equation on the right-hand side is translationally invariant, which means there must be some non-translational invariance in G plus, the Green's function. And this arises through this exponential here, where delta x1 is x1 prime minus x1. And an x2 bar here is the average of the second coordinate for the source and the sink. And the reason x2 bar is what breaks translational symmetry breaking is because of our choice of gauge, which is proportional to x2. Okay, so this Green's function has a translationally variant piece and a translationally non-invariant piece. And this is an infinite volume, which is fine because in infinite volume, the Chiral condensate is homogeneous, and Chiral condensates arise due to coincident Green's function. This translationally non-invariant piece vanishes, and all is good in the infinite volume theory. In finite volume, because of our choice of periodic boundary condition, we have to upgrade this delta function to be a periodic delta function. So now you have not just one winding, I should say not just x prime minus x, but also multiple windings around the box that has to be taken into account, because in the periodic box, x prime and x are equal up to these windings. So on the right-hand side is basically a delta function with compact support. And the solution is the infinite volume solution, except that there's this Wilson line. And I don't have a great argument as to why this is the solution, except to note that ultimately there's a covariant derivative hitting this Green's function. And because this is not a regular derivative, you need to dress it with appropriate gauge dependent operators that essentially ensures that this equation is satisfied. So one can sort of churn through the algebra of this problem and establish that this is the right solution. The key point, however, is the comment regarding coincident Green's function in finite volume. How does that behave compared to the infinite volume counterpart? So if you consider the coincident version, what you'll find is that there is a translationally invariant contribution, and there are two translationally non-invariant pieces that arise through these inverse Wilson lines, and the windings are nu1 and nu2. Okay. So now what we have is a scenario where the coincident Green's function is coordinate dependent. What does this coordinate dependent look like? And it turns out this answer lies in the quark condensate. The quark condensate is proportional to the charged Green's function. Why? Because, well, if you expand the Chiral perturbation theory Lagrangian, you'll notice that the term proportional to MQ has a pi 0, and a pi minus pi plus, right? So this is exhibiting the periodicity of the coincident Green's function. So for the lowest flux, so this is the lowest flux plot, there's a maximum here, there's a maximum here, and there's another maximum here, and there's a minimum in the center. So you're basically repeating within the size of the box. In the n phi equals 2, the second flux case, there is greater repetition. And then in the n phi equals yeah, and then for n phi equals, maybe this is, yeah, I don't remember now which one is this, but nevertheless, as you increase n phi, you notice that the translational symmetry breaking is slightly different, and this is manifested in the finite volume quark condensate. For large boxes, one can take the asymptotic limit. So in effect, you're taking the fixed flux scenario and making the box larger, which means the magnetic field is becoming weaker. And in doing so, you'll see the periodic structure arising from these cosines. So if n phi is 1, the solution repeats once. And if n phi is 2, the solution will repeat twice, and so on and so forth. The size of these corrections are exponential, and they're addressed by a power law. So in a finite volume calculation in a magnetic field, unlike in the absence of a magnetic field, the Chiral condensate is a spatially inhomogeneous entity, which is already a profound result. Lattice QCD, however, doesn't generally consider these because the statistics is pretty bad. The signal is pretty noisy. So what they typically do is they look at the averaged quantity. And the average quantity can be characterized by this ratio. So basically what one does is one takes the infinite volume result. So what is the size of the Chiral condensate shift as a consequence of the magnetic field? You put that in the denominator. And in the numerator, you average over the Chiral condensate and ask what the finite volume effect is. And the plot is shown on the right-hand side. And I'll go through this pretty carefully. So take a look at m pi L equals 3. Okay, so that is a box of size 4.5 Fermi. For the lowest flux quanta, you'll notice that the size of that ratio is slightly bigger than 20%, which is a significant finite volume correction, and the box sizes are not so small. So this is showing that if a magnetic field is turned on, and if you want to characterize finite volume effects, you have to be extremely careful, because finite volume effects enter at the same order in which the magnetic field effects enter. If you were doing this calculation at b equals 0, then you'd be comparing the Chiral condensate at leading order with a finite volume effect, which is a next to leading order, which is small and it's exponentially suppressed, and that's why one doesn't have to worry for the box sizes that we use currently. But here, what we are doing is looking at the impact of the magnetic field and magnetic field alone, which is quite significant. The other thing to notice here is that as you crank up the magnetic field, the size of this correction is going down. And the reason that should happen is because the Landau orbits are becoming smaller and smaller, so you feel the effect of the box less and less. So that's the reason this has to be going down. And the other thing you'll notice is that the dashed line, which is the asymptotic behavior that I exhibit here, this dashed line asymptotes basically to the same point. So all three lines are asymptoting the same line because in taking this large volume limit, we are fixing the flux. By fixing the flux, we're making the magnetic field small. So all of these different flux results are converging to the zero field result, which is as expected. If one looks at the detail, it's the behavior exponentially or behavior at asymptotically large boxes is an exponential times a power law, and the impact of flux is subleading. So basically, it gets washed out, which is consistent with what the plot is showing. And so with that, let me see if there are any questions. I'm running out of time, so I'll probably not go through all the slides I've prepared for you, but let's see if there are other questions first.
That's first. Thank you. Any questions from you guys? I mean, there were some already during the talk, but
Yeah, let me steer them for a second, see if they through on those.
so yeah, go ahead.
No, I think this might be quite an ignorant question, but you said that you're only working at tree level. So there's no loops or the alpha S involved. So is chiral perturbation theory, you said it's a kind of effective field theory, right? So isn't that related to renormalization, which involves things beyond tree level? So why use effective field theory?
Okay, that's a great question. So I should, clarify the discussion for the magnetic vortex lattices. These were done at tree level, and the reason these were done at tree level is because the dispersion relation in the presence of an electromagnetic background becomes extremely complicated, and so. Okay, so that's comment number one. The comment number two is it's not always clear how one does a next leading order calculation when inhomogeneous phases are present. So that's the other comment. So the only calculation in the set of talks that I've given where the analysis is purely tree level is for the magnetic vortex lattice. Everything else has to be at next to leading order because the effects are significant enough that if one wants to, for example, in the finite isospin case, compare against the lattice, one has to take into account the behavior of loops, what the loops are doing. Okay, and then the second comment is that for the thermodynamics and the magnetic field, remember, magnetic field interacts with pions, not at tree level, but at loop level, right? That's where the effect in the free energy manifests. So the analysis here again is at a next to leading order. So hopefully that addresses some of your concerns.
Yeah. No, I think I was just because I thought I heard you say at the beginning that everything was tree level, but maybe that was just
This was the other
specific slide.
Yeah. Everything for the finite isospin magnetic field is at tree level. Yes.
Okay.
Yeah, and I apologize for the lack of clarity. I think speaking early in the morning, I realize is much more challenging than I had imagined.
Yeah, there is. Coffee doesn't solve all problems.
Oh, absolutely not. Yeah, there's sort of, my speaking voice, it turns out, won't rise until the sun rises, right? So,
Yeah, I found actually how your condensates came out quite interesting. Would you mind actually sending me references to this part of it?
well, absolutely, yeah. So this is, I will send it to you, but this is all based on my work with Brian Taburzi, who's at City College, and the article is in PhysRevD. So I'll make sure I put that in an email as well. Yeah.
Because I clearly need to refresh my translation between chiral perturbation theory and QCD quantities on that level. Then, but okay, that's on me, right? But I find it actually quite interesting how intricate this starts off with how specifically tailored to a particular gauge. You have to start this off, and you get perfectly beautifully gauge invariant quantities out. Then that actually then have a periodic condensate that has a physical interpretation, right? This is very, very different from how you deal with lambda levels, for example, right? I mean, okay, you guys are aware of lambda levels. And they're a bit of a pain, right, in terms of interpreting
Yeah.
them. And this is
Absolutely. Mhm.
So that's
Yeah, I think, that's the beauty of gauge invariance, right? I mean, if you're looking at gauge invariant quantities, it better be the case that your choice of gauge not impact the physical structure.
what you're doing. And
Yeah.
so I just want for myself to revisit and review how this is happening here in this beautiful way. But that's what I have for us. If you don't have,
I also just on this plot as well. So remind me what the color represents in this.
Yes. So what am I plotting here? So let's go back. Okay. So so what I'm plotting here is the chiral condensate, which is proportional to the coincident Green's function. In the large volume limit, the corrections are exponential times some power law, and then there is the spatial varying structure that's encoded in the cosines. So what I'm plotting here is how, as I go from one part of the box to the other part of the box, how does the chiral condensate behave? And this behavior for large box sizes is periodic, and the repetition depends on the flux quanta you choose. So if n phi is 1, the periodicity in the x direction, right? Okay, so you go from 0 to L, and so the chiral condensate repeats itself. The same thing happens in the x2 direction. You go from 0 to L, the solution repeats itself. Now, if n phi were 2, then the repetition happens more often. It happens twice as fast. Okay, and so what I'm plotting here is the chiral condensate at different values of n phi. And I think it's n phi 1, 2, and 3, I think, but it's too early in the morning for me to actually.
it's actually the square brackets that you're plotting in a.
Right.
I must say you were just now very carefully saying for large boxes this goes periodic. Does this for if the box goes smaller, how does this distort?
Great question. So what I'm plotting here is actually the exact result and not the cosines, which is the asymptotic behavior. The large volume behavior encodes periodicity, but the exact result also encodes periodicity. And it turns out it's the same Jacobi theta function that I showed you earlier, except this is for a square lattice. So this is just one Jacobi theta instead of 2 for the triangular lattice, which is sort of an interesting trajectory in my own research career. The fact that I went from studying magnetic vortices to encountering lattice-like structures, even though these are not magnetic vortices. These are just the manifestation of finite volume artifacts.
Interesting. Cool. Yeah. More question. Don't see any, so let's thank you very much for an interesting second talk. I did have the fun that I was hoping for.
Yeah.
Despite this slight fever that I'm running. So you did me a good deal here.